I've been thinking a lot about time lately, and specifically about this idea that maybe, just maybe, time isn't this straight line that we always imagine it to be, stretching from the distant past through the present and off into some infinite future. What if, instead, time is a loop? What if everything that has ever happened and everything that will ever happen is destined to happen again and again and again in an endless cycle that has no beginning and no end? It sounds like science fiction, right? Or maybe like some ancient mystical idea that we've moved beyond with our modern understanding. But here's the thing, and this is what keeps me up at night sometimes. This idea isn't just philosophical speculation or religious mythology. It's actually something that serious physicists and cosmologists have considered, and in some versions of our best theories about the universe, it might even be possible. And that's both fascinating and deeply unsettling when you really think about what it would mean. Let's start with how we normally think about time, because before we can understand the loop idea, we need to understand what we're looping. When you wake up in the morning, you remember yesterday. You know that yesterday came before today, and you know that tomorrow will come after today. That seems obvious, right? It's so fundamental to how we experience reality that it's hard to even imagine it being any other way. We remember the past, we experience the present, and we anticipate the future. Time flows, we say, like a river, always moving in one direction, carrying us along with it from birth to death, from the Big Bang to whatever ultimate fate awaits the universe. This is linear time, and it's deeply embedded in how we think about cause and effect, about memory and identity, about purpose and meaning. Everything that happens, we think happens once. Each moment is unique, never to be repeated. Your 5th birthday happened once. This conversation is happening once. The formation of Earth happened once, 4.5 billion years ago, and it's never happening again. But what if that's wrong? What if this apparent flow, this seeming arrow of time pointing inexorably forward, is actually an illusion, or at least a local phenomenon rather than a fundamental feature of reality? You see, when you start digging into physics, when you look at the actual equations that describe how the universe works at its most fundamental level, time starts to look very different from our everyday experience of it. And that's where things get interesting, because the question of whether time could be a loop isn't just philosophical meandering. It touches on some of the deepest mysteries in physics, questions about the nature of the universe itself, about what happened at the Big Bang, about what will happen in the far future, about whether the laws of physics even allow for something like a time loop to exist. The weird thing is, the idea of time as a cycle isn't new at all. In fact, it might be one of the oldest ideas humans have ever had about time. Long before anyone knew anything about physics or cosmology, ancient cultures all over the world conceived of time as cyclical. Think about the Mayans with their complex calendrical systems that reset and begin again, or Hindu cosmology with its kalpas, these enormous cosmic cycles where the universe is created, exists for billions of years, and then is destroyed, only to be born again in an endless cycle. The ancient Greeks had this too, this notion of the great year, where all the celestial bodies would eventually return to their starting positions and everything would begin again. And you can see why this made intuitive sense to them, right? Because so much of what they observed in nature was cyclical. The seasons repeat, day follows, night follows day. The moon waxes and wanes and waxes again. Birth, life, death, and then new birth. The cycles were everywhere, and so maybe, they thought, time itself is just a much larger cycle, one so big we can't see the full pattern from our limited vantage point. But then something changed, and this is important for understanding how we got to where we are now in our thinking about time. Western philosophy and religion, particularly under the influence of Christianity, moved away from cyclical time toward linear time. Time had a beginning with creation, it progressed through history, and it would have an end with final judgment and the conclusion of all things. This was a fundamentally different way of thinking about time. History wasn't repeating, it was progressing towards something, towards some ultimate purpose or destination. And this linear view of time, well, it became deeply embedded in Western thought and eventually in Western science. When Newton formulated his laws of motion, time was this absolute thing, flowing uniformly from past to future, the same for everyone everywhere, a cosmic clock ticking away. And that made sense for the physics of his era, for calculating planetary orbits and trajectories and all of that. But here's where it gets really interesting, and where modern physics starts to challenge all of these intuitions. In the 19th century, this German philosopher named Friedrich Nietzsche came up with this idea he called eternal recurrence or eternal return. And it's one of the most fascinating and troubling ideas in philosophy. Nietzsche asked us to imagine that everything that has ever happened will happen again, exactly as it happened before. An infinite number of times, not just similar events, but the exact same events with the exact same people, the exact same thoughts and feelings and choices. You, reading this right now, have done this infinite times before and will do it infinite times again. Every joy, every sorrow, every mundane moment, and every profound experience, all of it recurring eternally in an endless loop. And Nietzsche thought this was the ultimate test of whether you truly loved life, whether you affirmed existence. Could you accept the eternal recurrence of everything, even the suffering, even the pain? Would you say yes to living this exact life over and over forever? Now, Nietzsche wasn't making a scientific claim here, right? He was making a philosophical and existential point about how we should live, about what it means to truly embrace life. But the interesting thing is that his idea, this eternal recurrence, isn't actually incompatible with certain interpretations of physics. And that's where we need to talk about what modern science has discovered about time. Because it turns out time is much stranger than Newton ever imagined. Einstein changed everything, and I mean everything, when it comes to our understanding of time. Before Einstein, everyone thought time was this absolute thing, the same for everyone everywhere, a kind of cosmic background against which events unfold. But Einstein's special relativity showed that time is relative, that it depends on your motion, that two observers moving at different speeds will disagree about how much time has passed between two events. Time, it turns out, is not absolute. It's part of the fabric of the universe itself, woven together with space into what we call space-time. And then general relativity, Einstein's theory of gravity, showed that massive objects warp space-time, that what we experience as gravity is actually the curvature of space-time itself. Time itself can be bent, stretched, compressed by the presence of matter and energy. And here's where things get really wild, because once you accept that space-time can be curved, that it can be bent and warped, well, then you have to ask, what shapes are possible? Could space-time curve back on itself? Could time form a loop? And the answer, surprisingly, is maybe. In the mathematics of general relativity, there are solutions called closed time-like curves, which are basically paths through space-time that loop back on themselves. If you followed one of these curves, you'd eventually return to your own past. Time, in these solutions, literally forms a loop. Now, whether these solutions correspond to anything real, whether they're physically possible rather than just mathematically possible, that's a different question, and we'll get to that. But the point is that Einstein's equations, our best description of gravity and space-time, don't rule out time loops. They don't say it's impossible. The physicist Kurt Gödel, who you might know as the mathematician who proved those incompleteness theorems, he found one of these solutions with closed time-like curves. In what's called the Gödel universe, space-time is rotating, and this rotation creates closed time-like curves everywhere. Time, in Gödel's universe, can loop back on itself. When Einstein learned about this solution to his own equations, he was apparently quite disturbed by it, because it seemed to violate something fundamental about causality, about cause and effect. If you can travel back in time, even in principle, then you run into all sorts of paradoxes, right? The grandfather paradox and all of that. But there it was, right there in the math, a universe where time could loop. Now, you might be thinking, okay, that's interesting as a mathematical curiosity, but we don't live in a Gödel universe. Our universe isn't rotating the way his solution requires, and you'd be right about that. But the existence of these solutions tells us something profound about the nature of time in general relativity. Time isn't this rigid, absolute thing. It's flexible. It's part of the geometry of space-time, and that geometry can take forms that seem deeply counterintuitive to us, forms that include loops and cycles. But let's step back for a moment and think about time in a different way, because there's this other aspect of time that we need to consider, and that's what physicists call the arrow of time. You know what I'm talking about, right? Eggs break, but they don't unbreak. Coffee cools down, but it doesn't spontaneously heat up. We remember the past, but not the future. There's this directionality to time, this asymmetry, where things happen in one direction, but not the other. And this arrow of time, it's connected to something called entropy, which is basically a measure of disorder or randomness in a system. The second law of thermodynamics says that entropy always increases in a closed system. Things go from ordered to disordered, not the other way around. A pristine room becomes messy, not the other way around, unless you put in work to clean it, and that work increases entropy somewhere else. This increase in entropy, this tendency toward disorder, is what gives time its arrow, or so the usual story goes. The past is the direction of lower entropy, the future is the direction of higher entropy, and that's why we can remember the past but not the future, why causes precede effects. But here's the puzzle, and it's a really deep puzzle that physicists have been grappling with for more than a century. The fundamental laws of physics, at least at the microscopic level, don't have an arrow of time. If you look at the equations that describe how particles interact, whether in classical mechanics or quantum mechanics or even relativity, those equations work just as well running forward in time as backward in time. They're time symmetric. There's nothing in the fundamental laws that says time has to flow in one particular direction. And yet, macroscopically, in the world we actually experience, time very clearly has a direction. Things evolve from past to future, not the other way around. So where does this arrow come from? The usual answer is that it comes from the initial conditions of the universe, from the fact that the universe started in a very low entropy state at the Big Bang. Entropy has been increasing ever since, and that increase is what gives us the arrow of time. But, and this is important, if the fundamental laws are time symmetric, and if the universe is or could be infinite or cyclic in some way, then you have to ask, where did those special low entropy initial conditions come from? Why did the universe start with low entropy? That's not explained by the laws themselves. And this is where the idea of a time loop or a cyclic universe starts to become really interesting from a physics perspective. Because if time is a loop, if the universe cycles, then you have this question, how does entropy work in a loop? Remember, entropy always increases. So if the universe is cycling, repeating, does entropy just keep increasing forever? That would seem to rule out a true cycle, because after enough cycles, entropy would be maximized and nothing interesting would happen anymore. Everything would be in a state of maximum disorder, thermal equilibrium, heat death. Or does entropy somehow reset at the end of each cycle, starting low again at the beginning? But how could that happen without violating the second law of thermodynamics? These are not easy questions, and they get at some of the deepest issues in cosmology and the physics of time. Let me try to unpack some of the different ways physicists and cosmologists have thought about cyclic universes and time loops, because there are actually several different models, each with its own fascinating implications and problems. One idea is what's called conformal cyclic cosmology, which was proposed by Roger Penrose, one of the great physicists of the 20th century. Penrose suggests that the universe goes through an infinite sequence of aeons. Each aeon begins with something like a Big Bang, and ends with something like heat death, where the universe has expanded so much and cooled so much that there's nothing left but extremely dilute radiation. But here's the clever part. In the mathematics of general relativity, there's a way to map the infinite future of one aeon onto the Big Bang beginning of the next aeon. The end of one cycle becomes the beginning of the next, not in time exactly, but through a kind of mathematical transformation. Time, in a sense, loops, though not in a simple way, where you come back to the exact same moment. Each cycle, each aeon, plays out similarly, but not identically. What's interesting about Penrose's model is that he's even suggested ways it might be testable. He's looked for evidence in the cosmic microwave background radiation, this afterglow of the Big Bang that we can still detect, looking for patterns that might be remnants from a previous aeon. Now, whether his evidence is convincing is a matter of debate, and most cosmologists are skeptical, but the point is that he's trying to make this more than just speculation. He's trying to connect it to observations we can actually make. Another approach to cyclic cosmologies comes from string theory and ideas about higher dimensions. In some of these models, our universe is like a membrane, a brain, floating in a higher dimensional space. And these brains can collide with each other, and each collision creates what looks to us like a Big Bang, a beginning of the universe. But from the perspective of the higher dimensional space, there was no beginning. The brains existed before and will exist after. Time, in the higher dimensional space, doesn't loop exactly, but from our perspective, stuck on one brain, each collision looks like the beginning and end of time, a cycle. These models can potentially avoid some of the entropy problems because each cycle isn't exactly a repeat. It's more like a new beginning with new initial conditions set by the collision. But let's think about what a true time loop would mean. Not just a cyclic universe where each cycle is different, but an actual loop where everything repeats exactly. This is closer to Nietzsche's eternal recurrence. For this to work, you'd need the universe to eventually return to exactly the same state it was in at some earlier time. And in fact, there's a theorem in physics, the Poincaré recurrence theorem, which says that certain kinds of systems will eventually return arbitrarily close to their initial state, given enough time. The caveat is that the system has to be isolated and bounded, and the amount of time required can be absolutely astronomical, far longer than the current age of the universe. But if the universe is finite in some sense, bounded in its possible states, and if it exists for infinite time, then Poincaré recurrence suggests that yes, everything will eventually repeat. You, me, Earth, the solar system, everything will eventually occur again. Not just once, but infinitely many times. The numbers involved are incomprehensible, truly staggering. We're talking about timescales like 10 to the power of 10 to the power of 120 years. Numbers so large they don't really mean anything to our intuition. But in an infinite timeline, even those unimaginable spans will pass and recurrence will happen. There's something deeply unsettling about this, isn't there? The idea that you're going to live this exact life again, make all the same choices, have all the same experiences over and over, and you won't remember the previous iterations because you'll be exactly the same as you are now, with exactly the same memories and lack of memories. From your perspective, each time through the loop is the first and only time, even though from some outside perspective, if such a thing could exist, you're repeating endlessly. This raises profound questions about personal identity and what it means to be you. Are you the same person in each iteration of the loop? What even makes you you if there are infinite copies of you living identical lives? And what about meaning and purpose? If everything you do has been done infinite times before and will be done infinite times again, does anything really matter? Or does the eternal repetition give everything a kind of absolute significance, each moment recurring forever, each choice echoing through eternity? Nietzsche thought that the eternal recurrence, even if it wasn't literally true, was the ultimate ethical test, a way to evaluate how you should live. If you had to live this day, this moment, exactly as you're living it now, over and over forever, would you be able to say yes to that? Would you be able to affirm it? Most people, he thought, would be horrified by the idea. The suffering would be too much, the meaninglessness too crushing. But the person who has truly overcome resentment and nihilism, who has achieved what Nietzsche called amor fati, love of fate, that person could embrace even the eternal recurrence, could say yes to life in all its joy and suffering, knowing it will all happen again, forever. But let's come back to the physics, because there's more to say about how time works at a fundamental level and whether loops are really possible. When you get down to quantum mechanics, things get even stranger. In quantum mechanics, time plays a very different role than it does in classical physics or even in relativity. Time is treated as a parameter, not as an observable like position or momentum. The Schrödinger equation, which describes how quantum systems evolve, has time in it, but time is absolute in standard quantum mechanics. It's not relative like in relativity. This causes problems when you try to combine quantum mechanics and general relativity, when you try to create a theory of quantum gravity. In some approaches to quantum gravity, time might not be fundamental at all. It might be what's called an emergent property, something that arises from more basic, timeless laws at the deepest level of reality. If that's true, then asking whether time loops at the fundamental level might not even make sense, because there might not be a fundamental time. What we experience as time, and as the flow of time, might be an emergent phenomenon that arises only at macroscopic scales, only in the realm of things we can observe and measure. But even in standard quantum mechanics, there are strange implications for the nature of time The famous double slit experiment shows that particles can behave like waves, interfering with themselves, and that the act of observation affects the outcome. But there are also delayed choice experiments where it seems like the present can affect the past, or at least our interpretation of what happened in the past. The physicist John Wheeler proposed thought experiments where you could decide, after a photon has passed through a double slit apparatus, whether to measure which slit it went through or to observe the interference pattern. And your choice now seems to retroactively determine how the photon behaved in the past. Now, this doesn't let you send information to the past or violate causality in any practical sense. But it does suggest that the relationship between past, present, and future in quantum mechanics is much more subtle than our everyday intuitions suggest. And then there's quantum entanglement, where particles can be correlated in ways that seem to transcend space and time. Einstein called it spooky action at a distance, and it bothered him deeply. When you measure one entangled particle, you instantly know something about its partner, no matter how far away it is. This doesn't violate relativity because you can't use it to send information faster than light, but it does suggest that space and time at the quantum level don't work the way we think they do. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that every quantum measurement branches the universe into multiple parallel realities. Time, in that view, isn't a single line or even a single loop. It's an endlessly branching tree of possibilities, all equally real. But back to loops. If time could loop at the quantum level, you'd have quantum systems returning to their earlier states, and this raises all sorts of paradoxes and questions. There's been work on what are called closed time-like curves in quantum mechanics, trying to figure out what would happen if quantum particles could travel in loops through time. Some researchers have found that quantum mechanics might actually be more tolerant of time loops than classical physics. In the classical world, time travel paradoxes seem insurmountable, but in quantum mechanics, where particles can be in superpositions of multiple states at once, some of these paradoxes might have solutions. A particle could be in a superposition of having and not having time traveled, for instance, and the math works out consistently. This is highly speculative, obviously, and we're nowhere near having the technology or even the theoretical framework to really test these ideas. But it's fascinating that our best theories of physics don't completely rule out time loops. They allow them as possibilities, at least mathematically, even if we don't know whether they exist in reality. Now let's think about causality, because that's really what's at stake here with time loops. Causality is the idea that causes precede their effects, that events in the past influence events in the future, but not the other way around. This seems like one of the most basic features of reality, right? You can't affect what's already happened. The past is fixed. But in a time loop, causality gets weird because effects can precede their causes, or rather, the distinction between cause and effect breaks down. If the loop is closed, if event A causes event B, which causes event C, which causes event A again, then which one is the cause and which is the effect? They're all both. This is sometimes called a causal loop or a bootstrap paradox. Imagine you go back in time and give Shakespeare a copy of all his plays, which he then copies and publishes as his own work. Where did the plays come from originally? They came from Shakespeare, who got them from you, who got them from Shakespeare, who got them from you, in an endless loop. The information has no origin, it just exists in the loop. This seems impossible, right? It violates our intuition that everything must have a beginning, a first cause. But in a time loop universe, maybe there are no first causes. Maybe everything is just part of the eternal cycle. The physicist David Deutsch has done interesting work on closed time-like curves and quantum mechanics, and he's argued that they don't lead to logical contradictions, though they do lead to strange situations. If you try to go back in time and create a contradiction, quantum mechanics will prevent you from succeeding. The universe will evolve into a state where the contradiction doesn't arise through quantum superposition or other effects. So time travel might be possible, but useless for creating paradoxes, which is weird, but at least consistent. But whether time loops are possible is different from whether they actually exist, whether our universe actually is a loop or part of a cycle. And to answer that, we need to look at what we know about cosmology, about the large-scale structure and evolution of the universe. The universe, as far as we can tell, began about 13.8 billion years ago in the Big Bang. Now, The Big Bang wasn't an explosion in space, it was the beginning of space itself and time itself. At least that's the standard story. The universe has been expanding ever since, cooling as it expands, matter clumping together under gravity to form galaxies and stars and planets. We can see this history written in the cosmic microwave background, in the distribution of galaxies, in the abundances of elements. The evidence for the Big Bang is overwhelming. But what happened before the Big Bang? That's where things get tricky, because if time itself began at the Big Bang, then asking what came before is like asking what's north of the North Pole. The question doesn't make sense, but maybe time didn't begin at the Big Bang. Maybe the Big Bang was a transition, a bounce from a previous contracting phase of the universe. In a cyclic model, the universe expands, reaches some maximum size, contracts back down, bounces and expands again. The Big Bang we observe would just be one bounce in an eternal series of bounces. For this to work, you need some mechanism to reverse the collapse and cause a bounce. In classical general relativity, a collapsing universe would collapse all the way to a singularity, a point of infinite density where the laws of physics break down. But quantum effects might prevent that. Quantum gravity, whatever form it takes, might create a kind of repulsive force at extremely high densities that stops the collapse and causes a bounce. This is speculative because we don't have a complete theory of quantum gravity, but it's not ruled out. One problem with cyclic bouncing models is entropy. If the universe keeps cycling, entropy keeps increasing, and after enough cycles, you'd end up with maximum entropy in every cycle, and nothing interesting would happen. The cycles would all be essentially the same, just boring thermal equilibrium. Some models try to get around this by having the volume of the universe increase with each cycle, so there's more and more room for entropy to increase, and the universe never quite reaches maximum entropy. But this means the cycles aren't true repeats. Each one is different from the last, which brings us back to the question of whether this is really a time loop or just a series of different epochs. Another challenge is explaining why our cycle, the one we're in now, has such relatively low entropy. If the universe has been cycling forever, we'd expect to find ourselves in a high entropy cycle where nothing interesting happens. The fact that we're in a low entropy cycle where stars can form and life can exist seems like it requires an explanation. Some cosmologists invoke what's called the anthropic principle, the idea that we can only observe the kind of universe that allows observers to exist, so it's not surprising that we find ourselves in a low entropy phase. But that explanation strikes many people as unsatisfying. What about the far future of the universe? Current observations suggest that the expansion of the universe is accelerating, driven by something called dark energy. If this acceleration continues, the universe will expand forever, growing colder and emptier, stars burning out, black holes evaporating through Hawking radiation, until eventually there's nothing left but a thin soup of particles in an unimaginably vast space. This is called heat death, or the Big Freeze. It doesn't sound like the setup for a cycle, does it? If the expansion keeps accelerating, the universe will never recollapse, never bounce, never repeat. But dark energy is mysterious. We don't really know what it is or how it behaves. It's possible, though most physicists think unlikely, that dark energy could change over time, that the acceleration could reverse, leading to a big crunch where the universe collapses back down. Or maybe there are other mechanisms, other physics we don't understand yet, that could lead to cycles. Penrose's conformal cyclic cosmology, which I mentioned earlier, tries to deal with the heat death by arguing that in the infinite future, when all the matter has decayed and there's nothing left but radiation, you can rescale the geometry of space-time in a way that maps that infinite future onto a new Big Bang. Time doesn't exactly loop in the usual sense, but the end of one aeon becomes the beginning of the next. It's a clever mathematical trick, and Penrose is a brilliant physicist, but it's fair to say most cosmologists are skeptical that this is how the universe actually works. There's also this interesting question about whether the universe is spatially finite or infinite. If space is finite, if you could travel far enough in one direction, you'd eventually come back to where you started, like traveling around the surface of a sphere, then the universe has a finite number of possible states. And if it exists for infinite time, Poincare recurrence tells us everything will eventually repeat. But if space is infinite, then there might be infinitely many possible states, and recurrence isn't guaranteed. Current observations suggest the universe is either infinite or so large that we can't see its curvature, but we can't be sure. Let me shift gears for a moment and think about what a time loop would mean for consciousness and subjective experience, because this is where it gets really philosophically interesting and honestly kind of disturbing. If time is a loop, if you're going to live this exact life infinite times, what is it like to be you? From the inside, from your subjective perspective, you're only aware of one iteration at a time. You don't remember previous loops because you're exactly the same as you were before, with exactly the same memories. Each time through feels like the first and only time. But in what sense are you the same person across iterations? This gets at deep questions about personal identity. What makes you you? Is it your memories, your personality, your body, the physical continuity of your atoms? In a time loop, there's no continuity from one iteration to the next, in the usual sense. The loop ends and then it begins again from the same starting point. You're not the same person in the sense of being a single continuous stream of consciousness. You're more like infinite copies, each living the same life, unaware of the others. Some philosophers would say these are different people, numerically distinct individuals who happen to be qualitatively identical. Others would argue they're the same person because there's no relevant difference between them. These debates get very abstract very quickly, but they matter if we're thinking about the ethical implications of a time loop. Do your choices matter if you're going to make them again anyway? Exactly the same. Can you be held responsible for actions that are going to repeat eternally? Determinism is relevant here too. If time is a loop, if everything repeats exactly, then in some sense everything is determined. You can't do anything differently because you're going to do exactly what you did before, every single time. This seems to undermine free will, at least in the libertarian sense, where free will requires genuine alternative possibilities. But maybe that's okay. Maybe free will is compatible with determinism, or maybe free will is an illusion anyway. These are old philosophical debates, but a time loop gives them a new, more visceral dimension. There's also something poignant, almost tragic, about the idea of eternal recurrence. All your joys and triumphs and moments of beauty will happen again, which might seem like a good thing. But all your suffering and pain and loss will also happen again, eternally, unchangingly. You'll never learn from your mistakes in any ultimate sense, because you'll make them all again. The universe has no memory, no progress, no growth. It's just the same pattern playing out forever. Or maybe, and this is what Nietzsche suggested, that's actually liberating in a way. If there's no ultimate purpose or goal, if everything is just eternally recurring, then the meaning of life is just life itself, the experience of it, the living of it. You're not working towards some future salvation or trying to avoid some ultimate damnation. You're just living, and that living, in all its complexity and contradiction, is enough. The eternal recurrence forces you to confront the question, do you love life enough to want it repeated forever? If not, maybe you need to change how you're living. But I'm getting philosophical, and I want to come back to the physics because there are some other aspects of time loops we haven't explored yet. One interesting thing about closed time-like curves is that they might create regions of space-time where chronology is violated, where the normal rules of cause and effect don't apply. These are called chronology-violating regions, and they raise all sorts of questions about whether the universe would allow such regions to exist. Stephen Hawking proposed something called the chronology protection conjecture, which is the idea that the laws of physics prevent the formation of closed, time-like curves, at least on macroscopic scales where they could be traversed by people or spaceships. The universe, Hawking suggested, protects chronology by making time travel impossible, not because of any fundamental law, but because of the way quantum effects work. Whenever space-time starts to curve back on itself enough to create a closed time-like curve, quantum effects would create infinite energy densities that would destroy the time machine before it could work. This is still just a conjecture, not a proven theorem, and some physicists think closed time-like curves might be possible after all. The Casimir effect shows that quantum fields can have negative energy densities under certain conditions, and negative energy is one of the things you'd need to create and stabilize a time machine. Whether you could get enough negative energy in the right configuration is another question, And most physicists are skeptical, but it's not obviously impossible. What about wormholes? These are another feature of general relativity, shortcuts through space-time that could, in principle, connect distant regions of space and time. If you could keep a wormhole open and manipulate its mouths in the right way, you could turn it into a time machine. One mouth ages more slowly than the other, say by moving it at high speed, and eventually you have two mouths that exist at different times. Go through one way, you travel to the future. Go through the other way, you travel to the past. But again, quantum effects might prevent this, either by collapsing the wormhole or by creating infinite energy densities. And even if you could make it work, you couldn't travel back to a time before the time machine was created, so it wouldn't let you loop time in the eternal recurrence sense. There's also the question of what physicists call global versus local properties of space-time. A closed time-like curve might exist locally in a small region of space-time, without the entire universe being a loop. You could have a time machine that lets you go back in time by a few hours or years, but the universe as a whole still has a beginning and an end, or at least a clear arrow of time. That's very different from a universe where time itself is a loop on the largest scales. In some speculative models of quantum cosmology, the entire universe might be described by a wave function that's timeless, where time as we experience it emerges from a more fundamental description that doesn't include time at all. The Wheeler-DeWitt equation, which is an attempt to describe the quantum state of the entire universe, doesn't have time in it explicitly. Time emerges from the correlations between different parts of the universe, from what's called entanglement. If this picture is right, then asking whether time is a loop might be the wrong question, because time isn't fundamental enough to have a global structure like a loop or a line. Let's think about observational evidence, because ultimately for a time loop to be more than just speculation, we'd need some way to test it, some prediction we could check against observations. Penrose's conformal cyclic cosmology predicts certain patterns in the cosmic microwave background, concentric circles that would be remnants of gravitational waves from colliding black holes in a previous aeon. Penrose claims to have found these patterns, but other researchers have been skeptical, arguing that the patterns are consistent with random fluctuations and don't require a previous aeon. The debate is ongoing, but it's an example of trying to make the idea testable. For a true time loop where the entire history of the universe repeats exactly, I'm not sure what kind of evidence you could look for. By definition, if we're inside the loop, we're going to observe the same things every time through. We can't step outside the loop to see it repeating. Any observation we make is part of the loop and will be made again in exactly the same way. So in some sense, a perfect time loop might be empirically indistinguishable from a one-time universe, at least from the inside. But maybe there are subtle effects, quantum signatures or cosmological anomalies that would hint at a loop structure. If the universe is cyclic in Penrose's sense, each cycle might leave traces that affect the next cycle, or if closed time-like curves exist anywhere in the universe, they might create detectable distortions in space-time or unusual quantum effects. These are the kinds of things physicists look for, but so far there's no strong evidence. Absence of evidence isn't evidence of absence, though. Just because we haven't seen signs of time loops doesn't mean they don't exist. Yet the universe is vast and strange, and there's a lot we don't know. Dark matter, dark energy, the quantum nature of gravity, the origin of the Big Bang, the ultimate fate of the universe, these are all open questions. A time loop might be part of the answer to some of them, or it might not. There's also the anthropic argument to consider. If some universes are loops and others aren't, and if loops are less conducive to the formation of complex structures and life, then we'd expect to find ourselves in a non-looping universe simply because that's where observers like us can exist. The fact that we observe a universe with a clear arrow of time, where entropy increases and stars form and planets develop life, might just be a selection effect. We're here because this kind of universe allows us to be here. But that argument assumes that loops are incompatible with life and consciousness, and that's not obviously true. If the loop includes the formation of stars and planets and life, then each iteration of the loop would have observers, and those observers would be us over and over. So the anthropic argument doesn't clearly rule out loops, it just raises more questions about what kinds of loops are possible and which ones could support life. Let me come back to the philosophical implications because I think they're profound and they touch on questions that science alone can't answer. If time is a loop, what does that mean for ethics, for how we should live? If everything you do is going to repeat forever, does that make your actions more significant or less? On one hand, each moment has infinite weight because it's repeated infinitely. Every choice echoes through eternity. On the other hand, nothing you do can change the pattern because the pattern is eternal. There's no ultimate progress, no final redemption or damnation, just the same cycle over and over. Different ethical frameworks would respond to this differently. A utilitarian might say that the eternal repetition multiplies the value or disvalue of your actions infinitely, so you should be even more careful to maximize happiness and minimize suffering. A virtue ethicist might focus on the character you're cultivating, which will be repeated eternally, and ask whether that's a character you can affirm. An existentialist might embrace the absurdity of it, the eternal recurrence of the same, and find meaning in the authentic living of each moment, even knowing it will all happen again. Nietzsche's response was to turn it into a kind of test. Imagine, he said, that a demon came to you and told you that you would have to live this exact life over and over forever. Would that be the greatest curse or the greatest blessing? Most people, Nietzsche thought, would be crushed by this news. But the Übermensch, the person who has overcome nihilism and resentment, who has achieved true self-overcoming, that person could say yes to eternal recurrence, could embrace it, could even wish for it. That's the ultimate affirmation of life. But there's something almost cruel about this thought experiment, isn't there? Because it takes away any hope of things getting better, any possibility of redemption or transformation. You are who you are, you've lived the life you've lived, and that's it forever. There's no second chance, or rather there are infinite second chances, but they're all identical to the first. The hope that most religions and philosophies offer, that there's some way to transcend or improve or reach a better state, that hope is closed off in a time loop. Unless, and this is an interesting thought, unless consciousness itself somehow transcends the loop. What if your consciousness, your subjective experience, persists across iterations in some way? Not as memory, because your memory resets each time, but as some kind of deeper awareness or accumulation of experience at a level beyond what we normally think of as consciousness. This is pure speculation, obviously, bordering on mysticism. But if there's some aspect of mind or awareness that exists outside of time, then maybe the eternal recurrence isn't just repetition, maybe it's a deepening or intensification of experience. Some mystical traditions have ideas like this, that the soul reincarnates but forgets its past lives, and through many lifetimes accumulates wisdom or karma. A time loop would be like reincarnation, but instead of progressing through different lives, you're repeating the same life, and maybe, just maybe at some level beyond conscious memory, you're learning something, becoming something, evolving even within the eternal repetition. But that's probably giving in to wishful thinking, wanting there to be meaning and progress, even in a scenario that seems to preclude it. The hard truth might be that if time is a loop, if everything repeats exactly, then there is no transcendence, no escape, no ultimate meaning beyond the meaning you find in the moment itself. And maybe, as Nietzsche suggested, that's enough. Maybe meaning doesn't need to be eternal or transcendent. Maybe the fact that we're here now experiencing this is sufficient, even if it's all happened before and will happen again. There's a certain kind of peace in that acceptance, if you can reach it. The pressure to achieve, to become something more, to leave a lasting legacy, all of that falls away if the universe is a loop. You can't leave a lasting legacy because everything will be erased and repeated. But you can live fully, authentically, intensely in each moment, knowing that this moment, in its eternal recurrence, is all there is and ever will be. Or maybe that's too bleak, too nihilistic. Maybe the fact that we can even conceive of a time loop, can worry about it, can find it troubling or fascinating, means that we're capable of a kind of awareness that transcends the loop, even if we're physically bound within it. Our imagination and our consciousness can reach beyond the confines of any particular moment or cycle, can comprehend the infinite, can ask questions about meaning and purpose that don't have easy answers. And ultimately, we don't know if time is a loop, We don't know if the universe is cyclic, or if our history will repeat, or if closed time-like curves exist. These are open questions at the frontiers of physics and cosmology. What we do know is that time is stranger than our everyday experience suggests, that the equations of general relativity allow for possibilities that challenge our intuitions, and that the nature of time is deeply connected to the biggest questions in science, questions about the origin and fate of the universe, about the nature of reality itself. The fact that time might be a loop, that eternal recurrence might be more than just a philosophical thought experiment, is both unsettling and awe-inspiring. It forces us to confront the limits of our understanding, the strangeness of the cosmos we inhabit, and the question of what it means to exist in a universe that might not care about our narratives of progress and purpose. Maybe the lesson, if there is one, is humility. Humility about how much we really know, how much we can know about the fundamental nature of time and reality. We've come so far in our understanding, from Newton's absolute time to Einstein's space-time to quantum mechanics and cosmology, but every answer raises new questions, deeper mysteries. The idea of a time loop sits at the intersection of so many of these mysteries, connecting the physics of space-time to the philosophy of existence, the mathematics of recurrence to the ethics of living. And maybe the point isn't to solve the mystery definitively, to prove once and for all whether time is a loop or a line or something else entirely. Maybe the point is the investigation itself, the asking of questions, the pushing at the boundaries of knowledge, the willingness to entertain ideas that challenge everything we think we know. That's what science is, at its best. Not a collection of facts, but a process, a way of engaging with the unknown, a commitment to following the evidence and the logic wherever they lead, even if where they lead is strange and uncomfortable and paradoxical. If time is a loop, if we're living in an eternal recurrence, then this conversation, these ideas, these questions, they'll happen again and again and again, forever. Does that make them meaningless, or does it give them a kind of eternal significance, each moment repeated infinitely, each thought and word echoing through the cycles? I don't know. I genuinely don't know. But I find something beautiful in the uncertainty, in the not knowing, in the fact that we can ask these questions even if we can't answer them definitively. The universe is under no obligation to make sense to us, to conform to our intuitions or our desires for clarity and certainty. It just is what it is, whatever that is. And we're part of it, not separate observers looking in from the outside, but embedded within it, made of the same stuff, subject to the same laws or lack thereof. If time is a loop, then we're part of that loop, caught in it, yes, but also expressing it, embodying it, experiencing it from the inside in a way that nothing else in the universe does, as far as we know. Consciousness is its own mystery, maybe as deep as the mystery of time. How does subjective experience arise from objective physical processes? Why is there something it's like to be us? And if time is a loop, what does that mean for consciousness? Does each iteration create a new conscious experience, qualitatively identical but numerically distinct? Or is there only one consciousness, one experience that somehow encompasses all iterations? These questions blend into each other, the physics and the philosophy and the metaphysics. And maybe that's appropriate, because maybe they're not really separate questions at all. When Nietzsche wrote about eternal recurrence, he was trying to find a way to affirm life in the absence of traditional religious certainties. God is dead, he famously declared, meaning that the old sources of meaning and value had been undermined by modernity and reason. But if you take away God and the afterlife and cosmic purpose, what's left? Nietzsche's answer was life itself, the will to power, the creation of values, and the ultimate test was whether you could affirm life even in its eternal recurrence. Could you say yes to existence, even knowing that all the suffering and meaninglessness would repeat forever? It's a demanding standard, maybe impossibly demanding. But there's something compelling about it, this idea that meaning doesn't come from outside, from some external source or ultimate purpose, but from within, from your own ability to create value and affirm existence. If time is a loop, if there's no escape and no transcendence, then that internal creation of meaning becomes all the more important, all the more necessary. And yet, and this is where I keep coming back to the uncertainty, we don't actually know if time is a loop. It might be. The physics allows it, at least in principle, but it might not be. The universe might have a beginning and an end, or a beginning and no end, or neither. Time might be emergent, not fundamental. Reality might be far stranger than any of our models suggest. The multiverse theories, for instance, where every possible universe exists, every possible history plays out in some branch of reality, that's a very different picture from a single time loop, but it's equally strange in its own way. What we're really up against is the limits of human understanding, the fact that our brains evolved to deal with medium-sized objects moving at medium speeds. And when we try to comprehend the very large or the very small, the very fast or the very slow, the beginning or the end of time, we're stretching our cognitive capacities to their limits and beyond. We use mathematics and logic and observation to extend our reach, to probe realities far beyond our direct experience, but there might be aspects of reality that are simply beyond our ability to conceptualize, no matter how clever we are. The idea of a time loop is already almost beyond comprehension, right? You can say the words, you can write down the equations, but can you really imagine it? Can you really picture living your life over and over, exactly the same, forever? I don't think I can, not really. My mind skitters away from it, tries to find some variation or some escape or some way to make it less absolute. But if it's real, if time really is a loop, then there is no escape, no variation, just the eternal return of the same. Physicists sometimes talk about the unreasonable effectiveness of mathematics in describing the natural world. Why should abstract mathematical structures correspond so precisely to physical reality? Why should the universe obey mathematical laws at all? Nobody really knows, but it does, and that effectiveness has allowed us to predict and understand phenomena far beyond what we can directly observe. But there's also a risk, which is that we start to confuse the map for the territory, the mathematical model for the reality it describes. Just because the equations of general relativity allow for closed time-like curves doesn't necessarily mean they exist in nature. Math is a tool, an incredibly powerful tool, but it's not the same as reality. So when we ask whether time is a loop, we need to be careful about what we're asking. Are we asking whether the mathematical models of space-time include loop solutions? Yes, they do. Are we asking whether such loops exist in our actual universe? That's much harder to answer, and we don't currently have strong evidence one way or the other. Are we asking whether the very nature of time itself, at the deepest level, is cyclical? That might depend on questions we don't even know how to formulate yet, questions about quantum gravity and the origin of space-time and the fundamental structure of reality. Each of these questions is legitimate, but they're different questions, and they might have different answers. And that's okay. That's how science progresses, by refining questions, by distinguishing between different possible meanings, by building models and testing them against observations. The process is slow and difficult and often frustrating, but it works, or at least it's the best method we have for understanding the natural world. In the meantime, while science continues its investigation, we're left with the philosophical and existential implications of the possibility that time might be a loop. And those implications are worth considering even if we never get a definitive scientific answer, because they force us to think about what we value, what we believe, what gives our lives meaning. If everything you do will happen again, infinitely, does that change how you should live? Does it make your choices more important or less? Does it make you want to live differently, to make different decisions, to embrace life more fully, or to resign yourself to fate? These aren't scientific questions, they're human questions. And they don't have right or wrong answers, only better or worse responses, more or less life-affirming attitudes. Nietzsche thought that the person who could embrace eternal recurrence had achieved the highest form of life affirmation, but maybe that's too much to ask. Maybe it's enough just to live as well as you can, to find meaning where you can, to love and create and explore and wonder, regardless of whether it's all happening for the first time or the infinite time. And there's something to be said for the attitude of curiosity and openness, the willingness to consider strange possibilities without immediately dismissing them or clinging to them too tightly. Maybe time is a loop, maybe it isn't. Maybe we'll find out someday, maybe we won't. Either way, the question is worth asking, the possibilities are worth exploring, and the mystery itself has a value that goes beyond any particular answer. I think that's part of what draws people to physics and philosophy. This sense that reality is deeper and stranger than it appears, that there are mysteries worth investigating, questions worth asking, even if they're hard or impossible to answer definitively. The idea of a time loop is one of those mysteries, sitting at the boundary between science and philosophy, testable in principle but perhaps not in practice, profound in its implications but uncertain in its reality. And maybe, in the end, that uncertainty is itself important, a reminder that for all our knowledge and technology and understanding, we're still small creatures in a vast cosmos, asking questions that might be too big for us, reaching for truths that might be beyond our grasp. But reaching anyway, because that's what we do, that's what makes us human. The eternal recurrence, if it's real, would mean that this reaching, this questioning, this wondering happens over and over, eternally. And if it's not real, if time is linear, and this moment happens only once, then maybe that makes the reaching even more precious, even more meaningful, because it's fleeting, ephemeral, never to be repeated. Either way, here we are, in this moment, thinking about time and loops and eternity, marveling at the strangeness of existence, trying to understand, trying to make sense of it all. And that, I think, is worth something, whether it happens once or infinite times, whether time is a loop or a line or something else entirely. The wondering itself is the thing, the questioning, the never quite satisfied curiosity that drives us to look deeper, to think harder, to imagine possibilities beyond what we can directly observe or easily comprehend. So what if time is a loop? What if everything that has happened will happen again, exactly as before, eternally? I don't know what the answer is, whether it's true or not, whether the universe works that way or some other way. But I know that the question matters, that it touches on something fundamental about existence and meaning, and what it is to be a conscious being in a strange and beautiful cosmos. And I know that the investigation continues, that physicists and philosophers and cosmologists are still working on these problems, still building better theories, still making new observations, still pushing at the boundaries of what we know and what we can know. And maybe that's the real answer, not a definitive yes or no about whether time loops, but an ongoing engagement with the mystery, a commitment to following the questions wherever they lead, an acceptance that some things might always remain uncertain while still being worth thinking about. The universe doesn't owe us answers, but it invites us to ask questions, and in the asking, in the searching, in the wondering, we find not just science, but meaning, not just facts, but wisdom, not just knowledge, but understanding. Whether time is a loop or not, that search, that questioning, that reaching toward understanding, that's what makes the journey worthwhile. Now let's move on to another theory for you to reflect on. I've been thinking a lot about endings lately, and not just any endings, but the ending, the final ending. The moment when everything, and I mean absolutely everything, stops. When the universe itself, this vast, incomprehensible expanse of space and time and matter and energy, when it all just ends. And the thing is, it's one of those concepts that seems almost impossible to grasp at first, right? Because we're used to things ending. We watch movies that end. We finish books. Relationships come to a close. Even our own lives have an ending that we all know is coming eventually. But the universe, the entire cosmos, how does something that contains literally everything come to an end? What would that even look like? What would it mean? And here's the really strange part, the part that keeps me up at night sometimes. The universe is ending right now, not in some distant abstract future, but right now, this very moment, as you're reading this. The process has already begun. The universe is dying, slowly, inexorably, and there's absolutely nothing that can stop it. That sounds dramatic, I know, and maybe even a bit frightening, but it's also, well, it's kind of beautiful in a way, because understanding how the universe ends, understanding what happens in those final moments, those last flickering instances before everything goes dark forever, it tells us something profound about the nature of reality itself. It tells us about time, about energy, about entropy, about the fundamental laws that govern everything that exists. And what scientists have discovered, what they've pieced together over decades of observations and calculations and brilliant theoretical work, it's stranger than anything you might imagine. The end of the cosmos isn't a single event, not really. It's a process, an unimaginably long, slow decline into darkness and silence, a gradual unwinding of all the complexity and structure that we see around us. until finally, after timescales so vast that they make the current age of the universe look like the blink of an eye, there's nothing left but empty space and quantum fluctuations. You see, when we talk about the end of the universe, we're really talking about the final consequences of something called the second law of thermodynamics. And I know that sounds technical and maybe a bit boring, but stay with me here, because this law, this simple, elegant principle, it's actually one of the most profound discoveries in all of science. It tells us that entropy, which is basically a measure of disorder or randomness in a system, always increases over time. Always. In any closed system, and the universe is the ultimate closed system, things move from order to disorder, from structure to chaos, from usable energy to unusable energy, and that's what's happening right now all around us in every moment. The universe is becoming more disordered, more random, more dead. Think about it this way. Imagine you have a hot cup of coffee sitting on a table in a cool room. What happens? The coffee cools down, right? The heat from the coffee spreads out into the room, and eventually the coffee and the room reach the same temperature. That's entropy increasing. The heat energy that was concentrated in the coffee, that was ordered and structured and useful, it spreads out, becomes diffuse, becomes useless. And you can't reverse this process, not really. You can't make the heat spontaneously flow back into the coffee from the room. It just doesn't happen. And that's because of the second law. Entropy always increases. Order always gives way to disorder. And when you scale this up, when you apply this principle, not just to a cup of coffee, but to the entire universe, you get something remarkable and terrifying. You get the heat death of the universe. Now, heat death is kind of a misleading term, actually, because it doesn't mean the universe gets hot. It means exactly the opposite. It means that eventually, after an unimaginably long time, all the energy in the universe will be spread out so evenly, so uniformly, that there won't be any temperature differences anywhere. And temperature differences, well, they're what make things happen. They're what drive stars to shine, planets to form, life to exist, thoughts to occur. Everything that happens in the universe happens because energy flows from hot places to cold places, from ordered states to disordered states. And when there are no more temperature differences, when everything is the same temperature everywhere, then nothing can happen anymore. The universe reaches a state of maximum entropy, a state of perfect equilibrium, and in that state, time itself, in any meaningful sense, stops. Not because time literally ceases to exist, but because there's no change, no events, no processes, just an endless, eternal, perfectly uniform stillness. But here's where it gets interesting, and this is something that I think a lot of people don't realize. The heat death isn't coming tomorrow. It's not coming in 1 billion years or 1 trillion years or even 1 trillion years. The timescales we're talking about here, they're so vast that they almost don't make sense. They're beyond human comprehension, really. The universe right now is, about 13.8 billion years old? That's the time since the Big Bang, since everything began. And 13.8 billion years sounds like a lot, right? It is a lot. It's more time than we can really grasp. But compared to the timescales of the universe's ending, 13.8 billion years is nothing. It's the tiniest fraction of a fraction. We're living right now in what cosmologists call the stelliferous era, the age of stars. And this era, this time when stars are forming and shining and dying, it's going to last for maybe another 100 trillion years or so. And even 100 trillion years, is just the very beginning of the end. You see, the universe has a future that stretches out, essentially forever, and scientists have actually mapped out this future in remarkable detail. They've divided it into different eras, different epochs, each one characterized by the dominant processes and structures that exist. Right now, we're in an era where stars dominate, where galaxies are full of bright, shining suns, where planets orbit those suns, where maybe, just maybe, life exists on some of those planets. But this won't last. Stars are burning through their fuel, converting hydrogen into helium, helium into heavier elements, and eventually they run out. They die. And when stars die, depending on their mass, they either collapse into white dwarfs or explode as supernovae and leave behind neutron stars or black holes. And gradually, over those 100 trillion years or so, all the stars in the universe will die. Every single one. The last star will flicker out, and the universe will enter a new era, the degenerate era, an age dominated by stellar remnants, by white dwarfs and neutron stars and black holes, slowly cooling, slowly fading, drifting through an increasingly dark and empty cosmos. And that's when things really start to get strange, because we're still nowhere near the end. The degenerate era itself will last for, well, cosmologists estimate maybe 10 to the power of 40 years. That's a 1 followed by 40 zeros. A trillion is 10 to the power of 12. So we're talking about timescales that are incomprehensibly longer than a trillion. And during this era, the stellar remnants, these white dwarfs and neutron stars, they'll just sit there essentially, slowly radiating away their heat into the void. White dwarfs, which are what stars like our sun will become, they're incredibly dense objects, about the size of Earth but with the mass of the sun. And they're held up by something called electron degeneracy pressure, this quantum mechanical effect that prevents the electrons from being squeezed any closer together. And they just cool. They go from white hot to red to infrared to eventually black dwarfs, completely cold, completely dead stellar corpses drifting through space. But even that's not the end, because matter itself, it turns out, might not be stable. There's this theory, and it's still just a theory, not proven, but there's this idea that protons, the particles that make up the nuclei of atoms, might not last forever. They might decay. Now, if protons do decay, and we're not sure they do, the timescale is enormous. The half-life of a proton, if they decay at all, is at least 10 to the power of 34 years, and probably much, much longer. Some estimates put it at 10 to the power of 40, or even 10 to the power of 45 years. But if protons do decay, then eventually, given enough time, all the matter in those white dwarfs and neutron stars and planets and asteroids and dust clouds, all of it will just disintegrate. The atoms will fall apart. The protons will decay into lighter particles, mostly positrons and photons and neutrinos, and those will just radiate away into space. And what you're left with is, well, nothing. Just empty space and photons and maybe some electrons and positrons floating around, getting further and further apart as the universe expands. And, oh right, the expansion. That's another piece of this puzzle, another factor that's shaping the universe's end. The universe is expanding, and not just expanding, but accelerating. This was one of the most shocking discoveries in cosmology back in the late 1990s, when astronomers realized that distant galaxies weren't just moving away from us, they were moving away faster and faster. And the reason for this acceleration, well, we call it dark energy, but honestly, we don't really know what it is. It's some property of space itself, some energy inherent in the vacuum that's pushing everything apart. And this means that as time goes on, galaxies will get further and further from each other. Right now, we can see galaxies billions of light years away. But in the far future, in trillions of years, any galaxy outside our local group, outside our gravitationally bound cluster, will have moved beyond our cosmic horizon. The light from those galaxies will be so redshifted by the expansion of space that it will become undetectable. They'll effectively disappear from view. And eventually, if dark energy continues to dominate, every galaxy will be alone in its own observable universe, with nothing else visible, just an endless black void in every direction. But let's get back to the matter, to those particles and remnants drifting through the expanding cosmos. Because there's another player in this story, something that might actually be the final form of matter in the universe, and that's black holes. Black holes are, well, they're strange objects. They're regions of space-time where gravity is so strong that nothing, not even light, can escape. And they form when massive stars collapse, or when matter accumulates in the centers of galaxies, or even theoretically in the very early universe. And black holes are remarkably stable. Once something falls into a black hole, it's gone, at least as far as we can observe from the outside. The information about what fell in, the details of the matter and energy, all of that seems to disappear behind the event horizon, the boundary beyond which nothing can return. And so you might think that black holes would be the final resting place of matter, that they'd persist forever, eternal monuments in an otherwise empty universe. But here's the thing, and this is where it gets really interesting. Black holes aren't actually eternal, they evaporate. This was discovered, or rather theorized, by Stephen Hawking back in the 1970s, and it's one of the most remarkable insights in theoretical physics. You see, quantum mechanics tells us that the vacuum, empty space, isn't really empty. It's fizzing with activity, with virtual particles constantly popping into and out of existence. Particle-antiparticle pairs appear for the briefest instant and then annihilate each other. This happens everywhere, all the time, and normally it doesn't matter much because the particles disappear so quickly. But near the event horizon of a black hole, something different can happen. A particle-antiparticle pair can appear right at the edge of the event horizon, and one of the particles can fall into the black hole while the other escapes. And from the outside, from our perspective, it looks like the black hole is emitting particles. It's radiating. This is called Hawking radiation. And the really weird thing about Hawking radiation is that it carries energy away from the black hole. The black hole loses mass. It evaporates. Now, for a large black hole, the kind that forms from a collapsing star or sits at the center of a galaxy, this evaporation is incredibly slow. The Hawking radiation is incredibly faint, far fainter than the cosmic microwave background radiation that fills the universe. A black hole with the mass of the sun would take about 10 to the power of 67 years to evaporate completely. That's a 1 with 67 zeros after it. Compared to that, the current age of the universe, 13.8 billion years, is basically 0. But given enough time, and we have all the time in the universe, literally every black hole will evaporate. Even the supermassive black holes at the centers of galaxies, the ones with millions or billions of times the mass of the sun, even those will eventually radiate away into nothing. The timescale for the largest black holes might be 10 to the power of 100 years, maybe even 10 to the power of 110 years, but it will happen. And when the last black hole evaporates, when it emits its final burst of Hawking radiation and disappears, that's when we truly enter the final era of the universe, what cosmologists call the dark era. This is the age of maximum entropy, the age when the universe has reached its ultimate fate. And what does the universe look like in the dark era? Well, it's mostly empty space. Vast, unimaginable expanses of nothing, expanding, always expanding, getting emptier and emptier. There might be some particles floating around, photons, neutrinos, electrons, positrons, the decay products of any matter that existed before. But these particles are so spread out, so diluted by the expansion, that they almost never interact. The density of matter and energy is essentially zero. The temperature is essentially absolute zero, though not quite, because there's still that faint glow of photons, redshifted by the expansion to wavelengths billions or trillions of times longer than anything we could detect today. And in this dark era, time, as we understand it, becomes almost meaningless. I mean, time still exists technically. Space is still expanding, particles are still moving, albeit very slowly, but there are no clocks, no processes, no changes that would mark the passage of time in any meaningful way. If you were somehow an observer in the dark era, which is impossible for all sorts of reasons, but if you were, you wouldn't see anything happening. You wouldn't see stars shining or planets orbiting or matter falling into black holes. You'd see nothing, eternal darkness and stillness. And this state, this maximum entropy state, it lasts forever. Or at least it lasts for as long as the universe exists, which might be forever. But wait, you might be thinking, is the heat death, this slow decline into darkness and maximum entropy, is that really the only possible ending for the universe? And the answer is, well, we're not entirely sure. The heat death, or the big freeze as it's sometimes called, is the most likely scenario based on our current understanding of cosmology and the observations we've made. But there are other possibilities, other ways the universe might end, and some of them are far more dramatic and far more sudden than the slow fade of the heat death. One alternative is the Big Crunch. This is the idea that the expansion of the universe might not continue forever. If there's enough matter and energy in the universe, enough gravitational pull, then eventually the expansion might slow down, stop, and reverse. The universe would start contracting. Galaxies would start moving toward each other instead of away. And as the universe got smaller and smaller, everything would get closer together, denser, hotter. Galaxies would collide and merge. Stars would be torn apart by tidal forces, and eventually all the matter and energy in the universe would be compressed back into an incredibly hot, incredibly dense state, similar to the conditions right after the Big Bang. And then perhaps everything would collapse into a singularity, a point of infinite density, and the universe would end in a final cataclysmic crunch. Now, the Big Crunch was once considered a serious possibility, back when cosmologists weren't sure whether the universe had enough matter to stop the expansion. But observations over the past few decades, especially those measurements of distant supernovae that revealed the accelerating expansion, they've made the Big Crunch seem much less likely. If the universe is accelerating, if dark energy is pushing everything apart faster and faster, then a Big Crunch isn't going to happen. But we can't rule it out completely because we don't really understand dark energy. We don't know if it's truly constant, if it will always have the same strength. Maybe dark energy could weaken over time, or even reverse. Maybe the acceleration could stop and turn into deceleration. It's possible, albeit currently not what the evidence suggests. And then there's an even more dramatic ending, something called the Big Rip. This is the idea that dark energy, instead of being constant, might actually get stronger over time. And if that happens, if the repulsive force of dark energy increases, then eventually it would overcome not just the gravitational attraction between galaxies, but all the forces holding things together. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets, then molecules, then atoms, then atomic nuclei, and finally even space-time itself would be ripped apart. This would happen at some finite time in the future, maybe 20 billion years from now, maybe 100 billion, depending on the properties of dark energy. And when the Big Rip occurs, everything ends abruptly. One moment, the universe exists. The next moment, nothing. Not even space-time. It's a complete and total annihilation of everything. Now, I should say the Big Rip is probably the least likely of these scenarios. Most of the evidence suggests that dark energy is what's called a cosmological constant, which means it has a fixed strength that doesn't change over time. But we can't be completely certain. We're still learning about dark energy, still trying to understand what it is and how it behaves. And until we do, the Big Rip remains a possibility, however remote. There's another ending scenario that's even more unsettling in some ways, and that's vacuum decay. This one is based on quantum field theory, and it has to do with the idea that the vacuum, the empty space that we think of as the lowest energy state, might not actually be the lowest energy state. It might be what's called a false vacuum, a state that looks stable but is actually metastable, meaning it could decay into a lower energy state, a true vacuum, under the right circumstances. And if that happens, if the vacuum decays, it would be catastrophic. A bubble of true vacuum would form somewhere in the universe and expand outward at the speed of light. And inside that bubble, the laws of physics would be different. The constants of nature, things like the mass of the electron or the strength of the electromagnetic force, they'd have different values. Atoms as we know them couldn't exist. Matter would fall apart. And as the bubble expanded, it would destroy everything it encountered, rewriting the laws of physics as it went. The scary thing about vacuum decay is that it could happen at any moment without warning. There'd be no way to see it coming because the bubble would travel at the speed of light. So the information about its existence would arrive at the same moment as the bubble itself. We'd have no time to react, no time to prepare. One instant we'd be here, living our lives. The next instant we'd be gone, along with everything else. The entire universe, as far as we could observe, would be wiped out. And the worst part? We can't rule this out. It's possible. Based on our current understanding of particle physics and the Higgs field, it's possible that our vacuum is metastable. Not likely, maybe, but possible. And that's a bit unsettling, isn't it? But let's assume, for the sake of argument, that vacuum decay doesn't happen, that the Big Rip doesn't occur, that the Big Crunch isn't in our future. Let's assume that the most likely scenario, the heat death, the slow decline into maximum entropy, is what actually happens. What does that really mean? What are the implications of living in a universe that's doomed to end in darkness and silence? Well, one implication is that everything we do, everything that happens, everything that exists, it's all temporary. Stars will burn out, black holes will evaporate, protons will decay, and eventually there will be nothing left. No record of our existence, no trace of our civilization, no memory of anything that happened in the Stelliferous era. All the art and music and literature and science and philosophy that humanity has created, all the joys and sorrows and loves and losses that we've experienced, all of it will be gone, erased by the inexorable increase in entropy. And that can feel I don't know, it can feel kind of pointless, can't it? Like what's the point of anything if it's all going to end anyway? But here's another way to think about it. The fact that everything ends, the fact that the universe is finite in its capacity to sustain complexity and structure, that makes the time we have more precious, doesn't it? We're living in an incredibly special time, cosmologically speaking. We're here in the age of stars, the age when the universe is full of light and energy and possibility. And yes, it won't last forever, but it doesn't have to last forever to be meaningful. The beauty of a sunset doesn't depend on the sun shining eternally. The love you feel for someone doesn't require that person to live forever. Meaning and value don't come from permanence. They come from experience, from connection, from the richness of the present moment. And there's something else, something that I find deeply moving about the whole story of the universe's ending. We can know about it, we can understand it. We're these tiny, fragile creatures made of stardust, living on a small planet, orbiting an average star in an ordinary galaxy. And yet, we've figured out the ultimate fate of the cosmos. We've used mathematics and observations and our capacity for reason to peer billions of years into the future and understand how everything will end. That's extraordinary. That's one of the most remarkable achievements of human civilization. We're the universe becoming aware of itself, understanding itself, contemplating its own mortality. Now, let's talk about some of the finer details, some of the more subtle aspects of the universe's ending that make the story even more fascinating. One thing that's worth exploring is the timeline in more detail, because the stages of the universe's decline happen on such vastly different timescales that it's hard to keep them all straight. Right now, as I mentioned, we're about 13.8 billion years into the universe's history. That's not very old at all, cosmically speaking. Stars are still forming, galaxies are still colliding and merging, there's still plenty of gas and dust around to fuel new generations of stars. But this won't last. Star formation will peak and then decline. Some estimates suggest that we're actually already past peak star formation, that the universe is making fewer stars now than it did a few billion years ago, and this decline will continue. The gas and dust will gradually be used up, locked into stars and planets and stellar remnants, and eventually, in maybe 1 trillion years, star formation will essentially cease. During this time, our own sun will go through its life cycle. In about 5 billion years, it'll exhaust the hydrogen in its core and start fusing helium. It'll expand into a red giant, probably engulfing Mercury and Venus and maybe even Earth. Then it'll shed its outer layers, creating a beautiful planetary nebula, and the core will collapse into a white dwarf, which will then spend trillions of years slowly cooling until it becomes a black dwarf. And this is the fate of most stars, the ones that aren't massive enough to explode as supernovae. They'll all become white dwarfs and then black dwarfs, cold and dark and dead. But what about the more massive stars, the ones that do go supernova? Well, they leave behind neutron stars or black holes. Neutron stars are incredibly dense, denser even than white dwarfs. A neutron star might have twice the mass of the Sun, but be only about 10 kilometers in radius. The matter is compressed so tightly that the protons and electrons merge into neutrons, hence the name. And neutron stars, like white dwarfs, just sit there and cool. They might rotate, emitting beams of radiation if they're pulsars, but eventually they slow down and fade. And black holes, well, we've already talked about how they evaporate via Hawking radiation, but let's dig into that a bit more because it's such a strange and fascinating process. Stephen Hawking's realization that black holes emit radiation was revolutionary, because before that, everyone thought black holes were, well, black. Perfectly black. They absorbed everything and emitted nothing. But Hawking showed that quantum effects near the event horizon lead to the emission of particles, and that this radiation has a temperature inversely proportional to the mass of the black hole. A very massive black hole has a very low temperature, far lower than the cosmic microwave background, which means it's actually absorbing more radiation from the universe than it's emitting. It's gaining mass, not losing it. But as the universe expands and cools, the cosmic microwave background will eventually become cooler than the Hawking temperature of even the largest black holes. And at that point, they'll start to lose mass, slowly at first, but accelerating as they get smaller. And here's where the math gets really wild. The time it takes for a black hole to evaporate is proportional to the cube of its mass, double the mass, and the evaporation time goes up by a factor of 8. This means that small black holes evaporate much faster than large ones. A black hole with the mass of the Earth would evaporate in about 10 to the power of 50 years. That's already an incomprehensibly long time, but it's nothing compared to the evaporation time of a supermassive black hole. A black hole with 1 billion solar masses would take about 10 to the power of 100 years to evaporate. And the truly gigantic black holes that sit at the centers of the largest galaxies, the ones with tens of billions of solar masses, they might last 10 to the power of 110 years or even longer. During this time, during the black hole era, as it's called, these black holes are essentially the last large-scale structures in the universe. Everything else has decayed or dispersed or collapsed. The black holes are the final repositories of organized matter and energy, and as they evaporate, they emit a faint trickle of particles, photons mostly, but also occasionally more massive particles like electrons and positrons, and even protons and neutrons as the black hole gets smaller and its Hawking temperature gets higher. And in the very final moments of a black hole's life, when it's down to a very small mass, the Hawking radiation becomes intense. The black hole heats up dramatically, and in the last fraction of a second, it explodes in a burst of high-energy particles and radiation, and then it's gone. The black hole disappears, and all the information about everything that fell into it over its entire lifetime, all of that is released in the final explosion. At least, that's what Hawking's later work suggested, to resolve what's called the information paradox. The information paradox, by the way, is one of the deepest problems in theoretical physics. It arises from the tension between quantum mechanics and general relativity. Quantum mechanics says that information can't be destroyed. If you know the quantum state of a system at one time, you can, in principle, calculate its state at any other time, past or future. Information is conserved. But if black holes truly destroy information, if everything that falls into a black hole is lost forever behind the event horizon, then information isn't conserved. And that would mean quantum mechanics is wrong, which seems unlikely given how incredibly successful quantum mechanics has been at predicting the behavior of matter and energy at small scales. Hawking's original calculation suggested that the radiation emitted by a black hole is purely thermal, which means it contains no information about what fell in. But later work by Hawking and others suggested that the information might actually be encoded in subtle correlations in the Hawking radiation, and that it's released as the black hole evaporates. This is still an active area of research, and we don't have a complete understanding of how it works. But most physicists believe that information is somehow preserved, even in black hole evaporation. Now, let's think about what happens after the black holes are gone, after even the largest supermassive black holes have evaporated away. We're now in the dark era, and the universe is almost entirely empty, but it's not quite empty. There are still particles, photons and neutrinos, and maybe some electrons and positrons, and if protons haven't decayed, maybe some protons and neutrons too. But these particles are incredibly spread out, diluted by the vast expansion of space. The average density of matter and energy in the universe is essentially zero, and the temperature is essentially absolute zero, though again, not quite, because there's still that background glow of photons. And here's a question that's kind of fascinating to contemplate. In this dark era, with almost no matter and almost no energy, is anything happening at all? And the answer depends on what you mean by happening. On large scales, the only thing that's happening is the expansion of space. The universe continues to grow, stretching the distances between the remaining particles. But on quantum scales, even in this nearly empty universe, there's still some activity. Quantum fluctuations still occur. Virtual particles still pop in and out of existence. And occasionally, very, very occasionally, real particles might be created by quantum processes. For example, if the universe is truly infinite in spatial extent, which we don't know for sure but is possible, then given enough time, quantum fluctuations could create anything, including entire universes. This is the idea behind Boltzmann brains, these hypothetical self-aware entities that spontaneously form due to random quantum fluctuations in an otherwise empty universe. It's an extremely speculative idea, and the probability of such a thing happening is infinitesimally small, but it's not zero. Given infinite time, even infinitesimally small probabilities become certainties. But let's step back for a moment and think about what all of this means for the concept of time. In the early universe, time had a clear direction. The universe was hot and dense, and it was expanding and cooling, and entropy was increasing. There was a clear arrow of time pointing from the past to the future. But in the dark era, in the state of maximum entropy, what does time even mean? Entropy is no longer increasing because it's already at its maximum. There are no clocks, no regular processes that mark the passage of time. One moment is essentially indistinguishable from the next. And so, in a sense, time stops having meaning, not because time itself ends, but because there's nothing to differentiate one moment from another. This is related to something called the thermodynamic arrow of time, which is the idea that the direction of time, the fact that we experience time as flowing from past to future and not the other way around, is intimately connected to the increase of entropy. We remember the past and not the future, because entropy was lower in the past and is higher in the future. But in a state of maximum entropy, there's no such distinction. Every moment is essentially the same, and so the arrow of time disappears. It's a strange thought, and it raises all sorts of philosophical questions about the nature of time and consciousness and experience. Speaking of consciousness, let's talk about that for a moment. One of the most unsettling aspects of the universe's ending is the implication for life and consciousness. Life, as we know it, depends on energy gradients, on the flow of energy from hot to cold, from ordered to disordered. Life is a process that creates local pockets of order, local decreases in entropy, by increasing the entropy of the surrounding environment. We eat food which is ordered and full of chemical potential energy, and we use that energy to maintain our bodies, to think, to move, to live. And in doing so, we generate heat and waste, increasing the entropy of our surroundings. Life is a temporary, local reversal of the universal trend toward disorder, but it requires a constant input of energy to maintain. And in the far future, as the universe approaches heat death, as stars burn out and energy becomes increasingly diffuse and useless, life will become impossible. Eventually, there will be no energy gradients left to exploit, no way to power the complex processes that sustain living organisms. And so, life will end. All life, everywhere in the universe, if it exists elsewhere, will eventually go extinct, and that means consciousness will end too. The universe will spend the vast majority of its existence devoid of awareness, devoid of thought, devoid of any observer to witness its empty, dark expanse. Now, some people find this deeply depressing, and I get that. The idea that consciousness is temporary, that it's a brief flicker in the cosmic darkness, it can feel like a kind of existential defeat. But I think there's another way to look at it. The fact that consciousness exists at all, the fact that the universe, through processes we don't fully understand, but which seem to be rooted in the laws of physics and chemistry and biology, has given rise to beings capable of self-awareness, of thought, of wonder that's miraculous. We are, in a very real sense, the universe understanding itself. We're made of atoms forged in the hearts of stars, and we're capable of studying those stars, of understanding how they work, of predicting their future and the future of the cosmos itself. That's not something to be taken lightly. That's profound. And maybe, just maybe, the fact that consciousness is temporary makes it more valuable, not less. The fact that we have this brief window, this cosmological moment to experience and learn and love and create, maybe that's what gives it meaning. If consciousness lasted forever, if there was an infinite amount of time to experience everything, would any particular experience matter? Maybe it's the finitude, the limitation, the transience that makes things beautiful and important. Now, let's talk about some of the uncertainties, the things we don't know about the universe's ending. Because despite all the progress we've made in cosmology and astrophysics, there's still a lot we don't understand. Dark energy, for one, is a huge mystery. We know it exists, we can measure its effects on the expansion of the universe, but we don't know what it is. Is it truly a cosmological constant, a fixed property of space itself? Or is it something more dynamic, something that can change over time? This matters a lot for the ultimate fate of the universe. If dark energy is constant, then the big freeze, the heat death, is pretty much guaranteed. But if dark energy can change, then other scenarios become possible. Maybe it weakens and we get a big crunch. Maybe it strengthens and we get a big rip. We just don't know. And then there's the question of quantum gravity. General relativity, Einstein's theory of gravity, works beautifully on large scales, describing the motion of planets and stars and galaxies and the structure of space-time itself. And quantum mechanics works beautifully on small scales, describing the behavior of particles and fields and atoms. But we don't have a complete theory that unifies these two frameworks, a theory of quantum gravity that describes what happens when gravity becomes important at quantum scales. And this matters for the very early universe, for the Big Bang itself, and also for the interior of black holes, and potentially for the ultimate fate of the cosmos. Maybe quantum gravity will reveal new possibilities, new ways the universe could end, or new structures that could exist even in the far future. There's also the question of whether our universe is the only universe. Some theories in physics, particularly those related to inflation and string theory, suggest that our universe might be just one of many in a vast multiverse. If that's true, then the ending of our universe, while significant for us and for any other life that exists in our universe, isn't the ending of everything. Other universes would continue to exist, each with its own history and its own fate. And maybe new universes are constantly being created, sprouting from quantum fluctuations or from the decay of other universes. This is highly speculative, of course, and we don't have any direct evidence for a multiverse, but it's a possibility that some scientists take seriously. And what about the Big Bang itself? We know the universe began in a hot, dense state about 13.8 billion years ago, and that it's been expanding and cooling ever since. But we don't really know what caused the Big Bang or what came before it, if anything. Was there a before, or did time itself begin with the Big Bang? And could something similar happen again? Could a new Big Bang occur in our universe or in some distant region of space, creating a new bubble of expanding space-time? These are questions that push at the very boundaries of our understanding, and we don't have good answers yet. There's also the matter of mathematical infinities and singularities. Both the Big Bang and the interior of a black hole are described by general relativity as singularities, points where the density and curvature of space-time become infinite. But most physicists believe that these singularities aren't real physical entities, but rather indicators that our current theories break down. When you get infinities in your equations, it usually means you're missing something, that your theory is incomplete. And so, understanding what really happens at the Big Bang or inside a black hole requires a better theory, a quantum theory of gravity that can handle these extreme conditions. And maybe that theory will also tell us something new about the universe's ending. Let's also consider the role of observation and measurement in all of this. In quantum mechanics, the act of observation plays a crucial role in determining the state of a system. Before you measure a particle's position, for example, it exists in a superposition of multiple positions simultaneously. It's only when you measure it that the superposition collapses into a definite state. This raises interesting questions about the far future of the universe. If there are no observers left, no conscious beings to measure or observe anything, what does that mean for the quantum state of the universe? Does it matter? Some interpretations of quantum mechanics suggest that observation is essential for the actualization of reality, while others suggest that the universe exists independently of observation. This is more than just a technical question in physics, it's a deep philosophical question about the nature of reality and our place in it. And then there's the question of complexity and self-organization. One of the remarkable features of the universe is that despite the second law of thermodynamics, despite the inexorable increase in entropy, complex structures can and do form. Stars form from collapsing gas clouds. Planets coalesce from dust and debris. Life emerges from chemical reactions. All of these are examples of local decreases in entropy, local increases in order and complexity. And they're possible because the universe as a whole is far from equilibrium. There are energy gradients, temperature differences, regions where entropy can decrease locally as long as it increases more in the surroundings. But as the universe approaches heat death, as it reaches maximum entropy and equilibrium, these opportunities for complexity disappear. No more stars can form, no more planets, no more life. The universe becomes simple, homogeneous, boring. But here's an interesting thought. Could there be forms of complexity that don't depend on traditional energy gradients? Could there be structures or processes in the dark era that we haven't thought of, that emerge from quantum effects or topological features of space-time or something else we don't yet understand. It seems unlikely, but we can't rule it out entirely. The universe has surprised us before with its richness and complexity, and maybe it will surprise us again with possibilities we haven't imagined. And speaking of things we haven't imagined, let's talk about the possibility of intervention. Right now, we're passive observers of the universe's fate. We can calculate and predict what will happen, but we can't do anything about it. We can't stop stars from burning out or black holes from evaporating. We're subject to the laws of physics like everything else. But what if, in the far future, intelligent civilizations become advanced enough to manipulate the fundamental laws of physics? What if they find ways to create new energy sources, or to reverse entropy locally on a large scale, or even to escape to other universes? This is the realm of science fiction, obviously, but it's fun to speculate. Could a sufficiently advanced civilization find a way to survive the heat death, to persist even as the universe fades into darkness? There's an idea called the Dyson Eternal Intelligence scenario, proposed by the physicist Freeman Dyson. He suggested that an advanced civilization could potentially survive indefinitely in an expanding, cooling universe by becoming increasingly efficient in its energy use. As the temperature of the universe drops, the civilization would slow down its thought processes, taking longer and longer to think each thought, but using less and less energy per thought. And because of time dilation effects and the properties of thermodynamics, it might be possible for such a civilization to experience an infinite subjective time, even as the objective time extends over the heat death of the universe. It's a beautiful idea, though most physicists think it probably doesn't work in our actual universe due to the properties of dark energy and the specifics of quantum mechanics. But it's an example of the kind of creative thinking that can emerge when we contemplate these ultimate questions. Another question worth pondering is the nature of entropy itself. We talk about entropy as if it's a well-defined, absolute quantity, but actually, it's a bit more subtle than that. Entropy is a statistical concept. It's related to the number of microscopic configurations that correspond to a given macroscopic state. A high entropy state is one that can be achieved in many different ways, while a low entropy state is one that can only be achieved in a few ways. And this means that entropy is, in some sense, subjective. It depends on how you choose to describe the system, what you consider to be relevant information. And this raises the question of whether the heat death is really an inevitable final state, or whether it's just a final state given our current understanding of what's relevant. For example, if there are aspects of the universe's state that we're not currently taking into account, hidden variables or degrees of freedom that we don't know about, then maybe what looks like maximum entropy from our perspective isn't actually maximum entropy from a more complete perspective. Maybe there are ways for the universe to continue evolving, to continue generating complexity and structure, even in what appears to us as a state of maximum entropy. This is speculative, obviously, but it's a reminder that our understanding is always provisional, always subject to revision in light of new discoveries. Let's also think about the role of symmetry and conservation laws. In physics, symmetries are deeply connected to conservation laws through something called Noether's theorem. For example, the symmetry of physical laws under time translation, the fact that the laws don't change from one moment to the next, leads to the conservation of energy. And the symmetry under spatial translation leads to the conservation of momentum. These conservation laws are fundamental to our understanding of the universe. But what happens in the far future, in the dark era, when there's essentially no energy left in any usable form? Energy is still conserved. Technically, it's still there, in the form of photons and particle rest masses and the expansion of space. But it's not usable. It can't do work. It can't create structure or drive processes. And so, in a practical sense, the universe is energy dead, even though energy is still conserved. And this brings us back to the question of what it means for the universe to end. Is the end of the universe the moment when the last black hole evaporates? Or is it the moment when entropy reaches its maximum? Or is it some other milestone, like the moment when the last conscious being ceases to exist? Or maybe the universe never really ends at all. Maybe it continues forever, expanding and cooling and becoming emptier and emptier. but never actually reaching some final state. These are philosophical questions as much as scientific ones, questions about what we mean by end and how we define the existence of the universe. There's also the possibility, slim but not zero, that our understanding of the laws of physics is wrong in some fundamental way. We've been surprised before. Newton's laws of motion and gravity were considered correct for centuries until Einstein showed they were just approximations, valid in the limit of low speeds and weak gravitational fields. And quantum mechanics revealed a whole realm of phenomena that classical physics couldn't explain. Maybe there's another revolution waiting, another fundamental shift in our understanding that will change how we think about the universe's fate. Maybe the heat death won't happen because of some process or principle we haven't discovered yet, but based on what we know now, based on the best evidence and the most successful theories we have, the heat death seems like the most likely ending. And what's remarkable is that we can know this, that we can peer so far into the future with such confidence. We've measured the expansion rate of the universe, the density of matter and energy, the temperature of the cosmic microwave background. We've observed distant galaxies and supernovae, calculated the lifetimes of stars and black holes, applied the laws of thermodynamics to the cosmos as a whole. And all of this points to the same conclusion. The universe is running down, entropy is increasing, and eventually everything will fade into darkness. And yet, even in the face of this cosmic decline, there's beauty. There's beauty in the intricate dance of particles and forces, in the elegant mathematics that describes it all, in the fact that we, fleeting beings in a universe destined for darkness, can understand these grand processes. We're part of the universe, and we're part of its story. And even though the story ends in silence, the chapters we're living through right now are full of wonder and meaning. So what do we take from all of this? What's the lesson, if there is one, in contemplating the final moments of the cosmos? Maybe it's that we should appreciate the improbable miracle of our existence, the fact that we live in an era when stars shine and planets orbit and life can flourish. We're living in the golden age of the universe, cosmologically speaking, and it won't last forever. But it doesn't need to. The meaning and value of our lives don't depend on eternal persistence. They depend on what we do with the time we have, on the connections we make, the knowledge we gain, the beauty we create and appreciate. And maybe there's something profound in the fact that the universe, through us, has become aware of its own mortality. We're the universe contemplating its own end. And in doing so, we're participating in something deeply meaningful, something that transcends our individual lives and even the life of our planet and our civilization. We're part of the cosmos understanding itself, and that understanding, that knowledge, that wonder, it matters. It matters even though it's temporary, maybe especially because it's temporary. Because think about it, right? The universe existed for billions of years before we came along, and it'll exist for untold trillions of years after we're gone. But right now, in this brief cosmic moment, there are beings on this small planet who can look up at the stars and understand what they're seeing. We can trace the history of the universe from the Big Bang to the present. We can predict its future all the way to the heat death. We can understand the life cycle of stars, the formation of galaxies, the quantum mechanics of black hole evaporation. We can wonder about dark energy and dark matter and quantum gravity. We can ask big questions about meaning and existence and our place in the cosmos. That's extraordinary. That's precious. And the fact that it's all temporary, that one day the last star will burn out and the last black hole will evaporate and the universe will fade into silence, that doesn't diminish the importance of what we're doing right now. If anything, it enhances it. So here we are, you and me, thinking about the end of everything. And it's a strange thing to think about, isn't it? It's humbling and awe-inspiring and maybe a little bit frightening. But it's also, in its own way, beautiful. The universe has given us the capacity to understand it. And in using that capacity, in pursuing knowledge and asking questions and seeking answers, we're fulfilling something fundamental about what it means to be human. We're creatures of curiosity, and the universe, for all its vastness and indifference, invites that curiosity. It rewards it with insights and understanding and moments of profound revelation. And maybe that's the final thought to leave you with. The universe will end, we will end, but in the meantime, we get to be here, to witness and understand and participate in this grand cosmic drama. We get to look out at the stars and know that we're made of the same stuff, that we're intimately connected to everything we see, that we're part of something unimaginably large and ancient and beautiful. And that knowledge, that understanding, that sense of connection and wonder, it's a gift. A temporary gift, yes, but a gift nonetheless. And perhaps, in the end, that's enough.